Alrighty, I think we are back. If I didn't screw something up on all of this, let me double check. Man, this thing really does not like Safari. This, cool. Okay. So where do we end before I have to run out for lunch? Okay, we have this verifier function. It's getting pretty ugly, so I think I'm just going to start a little bit of basic refactoring. Let's make some structs. Let's call this ZODA prover commitment. Let's say T. Just this one, just for fun. Let's call this ZODA prover commitment equals ZODA prover commitment 1. Okay. This is going to include X. Actually, it's even going to include X tilde because that is good. We're going to use this instead of using X. Great. And now, instead of returning this thing, we could say that the ZODA prover commitment has, it's just this. Great. And this can get turned into ZODA prover commitment, and then let's call new thing a struct of ZODA verifier commitment, and that's, we don't need T here actually. What we do need is we need that, or what do we actually call these? Or Merkle row and Merkle column. Let's call this prover stuff. Oops. Verifier stuff. Merkle root. So it's not Merkle root, it's going to be binary batched Merkle tree.Merkle. I believe that's what it's going to be. Let's double check that before I fuck it up. Oh, actually, we do export Merkle root. Never mind. Great. I don't even have to do this. That's awesome. Bless you, Andrea, for coding this like insane Merkle root library. You are the best. Okay, and let's make this verifier. Oh, this is gonna not like me after doing this. Shit, that's fine. So one unfortunate part is why I am a little bit annoying about structs right now is because the Julia revise is quite particular about how structs are handled. And it's just like kind of an internal representation thing in Julia. So you have to do this trick. So every time we change a struct, when it is called, so it should be verifier commit. Right. Every time it is called, it will compile the struct in some way, and essentially, like if you change that struct, it will not like that. So actually, I will say it's kind of funny. I actually don't know why that's true specifically, but somebody should figure that out. Never really questioned that one. Okay, so cool. We are so back. Let's call this ZODA verifier commitment, and we are good on that. And this will be get roots, Merkle row, and get root Merkle column, and great. And let's make one more struct. No, I won't do that actually. That's too much fucking work. Okay, so now if we do commit of X tilde, we should get something quite neat and interesting. Oh no. Okay, so let's see. Expected union all. This is batched Merkle tree. So this is very silly because batched Merkle tree does not have a type, and I just trusted the AI god, and for that I have been punished. Okay, So, right, I now need to go to live type module. Right, it's also not batch Merkle tree. This is, what is it called? Complete Merkle tree. There we go. Great. Now if we do that, we should get a neat version, which is ZODA prover commitment alt type hex tilde. Is that what I need? I think we can play now. Yay! Great. In reality, I could, just not do that dumb thing, but that's fine. Okay, so now if we look at ZODA prover commit and ZODA verifier commit, let's do this one more time. Now we can check type of, I could make we need to make the pretty printing nicer and all that stuff for like these commitments, but I will not do that now. So if you look at type of ZODA prover commit, we get a prover commitment 1, which is this thing, and then once we do that, we can do the same thing for the verifier. ZODA verifier commit, and you get verifier commitment, which is exactly what I wanted. Okay, so far so good. All we're just doing is just restructuring all this stuff, so that's neat. Now we can just replace this with Z, prover commit, and this is ZODA prover commitment. T where T. So now I can do like encoding proof, and then I can do ZODA prover commit, and then R, and I'm just going to use, just so we're consistent on the mixing R for now. And now we can do encoding proof, and we can do ZODA prover commits and R and R prime or something. Great. And oh crap. Oops. I need to do this. Prover commit dot x tilde and then prover commit dot x tilde prime. And now we get the result we expect. So let's also wrap this also around a struct. So ZODA encoding proof 1 T. Oh, look at that. Wow. So nice of you, AI God. ZODA encoding proof equals ZODA encoding proof 1. And we can just wrap this. So T, we already have T actually. So we can do ZODA encoding proof. And do that. We now receive a ZODA encoding proof 1, which is awesome, or an alias for ZODA encoding proof. And finally, we can just redo all this insane nonsense. So this should be way cleaner now. What do we have? We have the verify. So to verify, we need the verifier commitment and a ZODA encoding proof. So let's call verifier commitment is a ZODA verifier commitment. I'm going to just do this just to make life a little bit cleaner. Yeah, I should do like something weirder than this, but whatever. Okay, the verifier encoding proof is going to be a ZODA encoding proof of type T, where T. S and S prime. Let's call these. Let's see. We should be able to have a Merkle root, a batched Merkle proof. Problem with the batch Merkle proof is it actually doesn't have the queries inside of it, which is rather annoying. So let's call this a ZODA Merkle proof. So a ZODA Merkle proof will essentially have the queries that you used. It will also contain the opening paths for the Should we do that? Is that too annoying, complicated? Should there be a better abstraction here? Because in reality, S and S prime are known to the verifier, which I would like to keep as a verifier structure. And ZODA Merkle proof could point to S and S prime because the ZODA Merkle proof does not make sense without them, but I also do not want to count that towards the communication cost, so I'm just thinking of like how to structure this. Let's see. All right, I'm going to elide this for now. This is going to be a Merkle, what do we call this? Gosh, Merkle proof. Actually, it's very annoying that Julia is not fully loading automatically right now for some reason or another. Probably, I'm going to do something silly here, which is, let's just restart this. Okay. I also have an old version, which probably is like 99% my problem, but that's fine. All right, using ZODA tensor, using binary fields. Great. Okay. There we go. That looks like it actually worked. So let's just do the same thing again we had before, and I should probably just put this into script or something, but 32 to the 10, and then we can do just commit ZODA, just neat, boom, and we can do prover com, verifier com equals whatever this thing is. Let's just call it answer for now because it's fine. I really need to pretty print the stuff. I'm just actually, well, the AI got pretty print for me. Function show. Oh, nice! Look at that. I mean, I don't actually. I think that's actually terrible, but also this doesn't actually even parse, which also is great, but what it really wants to do is this. Okay, so, you know, the AI god kind of understands Julia. That's good. Great. So now if we do this. Nice. Look at that. Great. And ideally the same is also true here. Base.show. Nice. Wow, that's so neat. Thank you. Whatever model is currently running, which is like some weird variation of probably 4.0. Whatever. Okay. This isn't even necessary, so let's do that. Okay. So we've got this. Let's continue on the verify function. So now actually if we, run the original thing we ran here, prover com, verifier com, we should just get, a tuple of things that doesn't suck. That's awesome. In reality, I would also print, some information about this thing as opposed to just like this thing is a prover commitment. And finally, let's do the verify. So verifier commit is good. We don't need that anymore, which is neat. It would be very nice to have this. So let's do this. Actually, we don't really. Now, let's have this. And then CWR. Great. So that's the verifier. This is not verifier. This is verifier. Yep. Okay. that's also, yeah, I should probably be checking, make sure that you guys are not, you know, posting nonsense or whatever. Or if you are, at least it's enjoyable nonsense. Let's see, I'm gonna pop up chat. Okay. Okay, so we are here with the verifier. We are doing all sorts of cool, neat, sick stuff. What are the openings? Oh yeah, right. So we have S prime, Merkle opening proofs. Man, I should probably make an encoding object, shouldn't I? Okay, let's do it. I'm gonna stop being a pain in the ass about this. Let's create a function which is opening proofs. We're just going to do the prover commitment SNS prime. Yes, thank you. Wow, you are so nice. This is so neat. It's not Merkle opening path though. It is, I believe, prove, which is probably not super apt name, and we should definitely fix prove. Let's do batched Merkle proof. I think this should work. We don't need this. Okay, let's see. So let's set S v1, 3, 5, 7 or something. I would like to make x of S is going to be what do we call this? Prover com.x s. So we're getting the S rows of the prover commitment, which is the big matrix that's already been encoded. We then need to prove that these are indeed in the Merkle row commitments. So it is going to be prove of prover com dot Merkle row, and then we need to prove that S. And this will be batched. Oh, right. So using batched the tree. There we go. Prove. Actually, do we even have prove here? No, actually that's great. So we just use prove. Prover com dot Merkle row, and then we should be able to use S here directly. Perfect. And we get a batch Merkle proof. So cool. Okay. So by the way, so you know S is of size 4 here, right? So actually, let's do something that's less dumb. Let's say we have rand 1 to the 12, and let's say we have let's say 150 samples. Actually, this is roughly speaking, and then let's sort S, and then let's make length. I just want to make sure that we don't have any duplicate entries. So length of S, or set S. So 146. So unfortunately, we do have duplicate entries. Shit. Let's try that again. 145. No. Let's just do this actually. So SP is collect of set S. So it's going to be duplicate entries, and then we're going to sort S. Okay, so S is now a vector of 145 elements, which is like roughly right. It's 148, but okay. So what we are going to do? Okay, so what are we doing? We're like need to like prove a bunch of openings. So we're going to open some rows, and we're going to prove their openings. So naively, for each row, you would take one path from the leaf to the root. But what happens and what's like interesting is if you think about it, you have a bunch of leaves which are all uniformly spread out. So they're everywhere kind of in this big Merkle tree. And if you like look at the number of times you repeat different leaves, right? So, okay, what is a Merkle proof? You open a leaf of the tree, you look at the neighbor, and then you use that neighbor on the tree to like construct, that is the proof, right? Because if, you know, I open up, say we have a Merkle tree of 4 leaves, I open up leaf 3, what do we do in a Merkle tree? We take leaf 3 and leaf 4 and hash them. That creates like, you know, the second leaf in the first level, which you then hash with its neighbor to get the highest leaf. So what do you need to construct the root based on the hashes of this? You need every neighbor, you know, on the path all the way to the root, you need every neighboring hash. So that's fine if you just have one opening, right? If you're just opening one leaf, we're totally chilling. Yeah, part 2, we are so back. But in reality, we're actually going to open about 150 such entries. So what that means is if you like think about the naive version, if you were just to open a leaf and then look at the path and then look at the neighbors of that path, you do that for one leaf and then you do that for the other leaf, well, certainly you're going to have overlap. Here's the dumbest version of overlap. Certainly you're going to like the second level, the one right below the root, you're going to copy at least once, because you will either one of the leaves lies in one half of the tree and the other one lies in the other half of the tree, in which case you already know those hashes, or both of them lie on one side of the tree and you're sending the same information twice. So when you have 2 elements, you already are guaranteed to save at least one hash, which is the second highest point, right? But you can imagine as you like get more and more elements, what's happening is like you end up getting a bunch of parts of the tree that you can then sometimes, but not always, reuse for the next query that you're going to open up. And so what batched Merkle trees does, essentially, it opens all of them at the same time, quote unquote, by keeping track of what neighbors are necessary, what additional neighbors are necessary to compute the next path root. So the next path to the root, right? And essentially every time you already have a hash that you had previously, so if you already have, for example, like, you know, the root you obviously have, but in the second path, once you have that, it will not send that new hash again, because it already knows that you had, like, to have proven the previous iteration, you had to have known what that hash was. So anyways, that's the like high level idea, and that's what batch Merkle proofs does. So the comparison is, just to really hammer the point home, the naive version is going to be S times the tree height, I believe is what it's called, or what is it called, Merkle? The get depth. So get depth of prover commitment dot Merkle row or whatever. So oops, length S, right? So the number of hashes that you're going to be providing here is a 1740, right? And multiply that by 32 bytes per hash, you're eating 55 kilobytes worth of proof. Here, that's actually fine, because it turns out that the like encodings are way larger than the batch Merkle tree. But like, so this would be the naive approach. If you don't do the naive approach, so if you do what we did here, right? What you should get is well, let's see. Let's hope we get the right thing. And proof equals prove, and then let's just do prover com Merkle row, and then we should be able to do S. Oops. That's what I guess when I don't use tab complete. Okay, and then if we do size of and proof, it should give us it's 19 kilobytes, which is substantially like the reduction here is naive proof size is this, right? And naive proof size divided by size of and proof is, so it's a reduction of about 2.9 times. Again, this doesn't really matter, because here the proof size, the things that we're actually going to send, these YR and WR prime, are going to be roughly on the order of about 800 kilobytes or so. So this is negligible proof size, but it's nice to save a little bit. This really is actually very important, not in ZODA, but it is very, very important in the Hirito. because of the number of hashes that we actually do is actually fairly non-trivial. So it is, yeah, it's worth doing this kind of stuff every once in a while, taking a step back and being like, how can we make these batch Merkle proofs more efficient and stuff. And the point is, this is already happening magically and automatically from the batch Merkle proofs library that Andrea and I, and by that I mean 99.9% Andrea and I think I changed like a name or something, wrote. So okay, so we are here. We have the Merkle opening proofs. These are not batch Merkle proofs. Actually, these are tuples of this because we need one for the rows and one for the columns. And then we have openings. So if I recall correctly, we should be able to do this. So let's do this. Okay. So what do we need to do? We're going to need to open the rows via S. We need to open the columns via S prime. We do not need prove here. Great. And then we return these opening paths here, which are awesome. This will be the Merkle opening proofs. Let's actually make a struct here. Let's call this ZODA row openings, or ZODA row call openings, maybe. Okay, and then let's call this struct T. So we're not going to pass, S is not going to be part of this because S is known to the verifier. This is going to be just like what the prover gives to the verifier once the verifier requests S and S prime. That will be, let's see. So what do we need? We will need the Merkle opening proof. So row opening proof. So first of all, row openings, which should be a matrix of type T. Same thing with column openings. And then we need the row opening proof, which is going to be a batch Merkle tree, batch Merkle proof, and the same thing with a column. So that should be good. So opening, or let's call this row call openings. We take the prover commitment, we take S and S prime, and then we're going to do the, let's call this row opening proof, call opening proof. All right, great. And just to be a little bit more annoying, I know this is not going to be consistent with the comment we have earlier, but that's fine. Let's call this row and S call. In the paper, this is going to be S and S prime, but here we'll just call it S row and S call. So let's see. Any questions, ideas, notions, constructions, vibes? Nope. Seems like everyone understands 100% of everything that is happening. Perfect. So, okay. So where are we at? Let's start with, sorry, I don't know why I'm making such a big deal out of this. This is like very dumb. Like even freaking ChatGPT is telling me like you're being an idiot. So okay, let's call, so we need n, which is going to be the size of x tilde, so there's actually going to be the things that we care about. The row openings are going to be prover commit dot x 1 to n, and then the call openings are going to be collect this transpose. So like, you know, given our conversation earlier in funnily enough in on Twitter or X or whatever, what happens here when we actually write this transpose is there's the transpose is actually not materialized. So this is cool and sometimes very annoying. It's mostly cool because in reality you almost never need to actually materialize the transpose of a matrix, except in this case where we actually need to provide column openings and we need to provide them as a matrix. So what we are doing here is we are going to take the columns, right, which are the things that we care about, and then we are going to commit to, or we are going to take those columns, take the transpose, right? So we subsample the columns, take the transpose, but if you actually think of what's happening in the memory, like in memory, like these columns are like laid out in one line. When you take the transpose, you now need to kind of copy the like rows corresponding now to the columns of the transpose. So you need to call collect, which is actually a pretty expensive operation, although we don't care right now because we're not really going for super duper fast. We're just going for a thing that looks roughly like the paper. Okay, and so anyway, so with that, now we have everything we need, and we can just do ZODA, row openings, row call openings, and a T, and we just, all right, great. And it seems to be very happy with what it's wrote. So if we call, let me also export this row call openings, and let's just also verify, although that will conflict. So let's just start with that for now. Oh, and let me do this annoying trick that we unfortunately do have to do. ZODA. All right, so I'm going to use S for the same one here. It's just rather silly, but so row call openings should be a cool, neat function. Let's do the prover commitment, and then let's do S, and let's do S twice. Oops. S is not defined in ZODA tensor because I am an idiot. Row call, and everything's good. Great. No. There we go. S is not defined as, oh, did I forget to save? I did forget to save. Great. So now we have this, and just also for fun, let's do base.show. Great. Glad we can all agree. Sick. Cool. So now we have a bunch of opening proofs for all this stuff, which is super neat and super cool. Let's write it all. So, by the way, like, I will apologize. I have never coded a cryptography library in Rust or anything, but we are like 99% of the way towards a prover and a verifier here with fairly. I don't know how much it'll work, but let's say the previous stream was 80 minutes, and I think something like 40 of them were me babbling. This stream is hopefully not too much longer. And we are already most of the way towards a complete prover and verifier. Yeah, is it, ready to release? No, absolutely not. Is it like all this stuff? Like, absolutely not. But it's a working thing, which very clearly mirrors the code. And so my point is like this tells you something kind of interesting about like the abstractions that we have chosen here, because the code is, 100 and this is like, or not even 100 lines of code with a bunch of white space and stuff. And yet here we are sitting around just like typing up the obvious things that we need to get, how we need to get them, putting them in little structs, and then passing them around. So it's just worth like keeping in mind, abstractions do matter for better or worse. And so it's one of these things where it looks, I'm a pain in the ass about these things because it obviously first because it's fun, but actually because I do think these things really do matter. And sometimes we go too far down the rabbit hole of we try to retrofit to what we have, and sometimes it's just better to not do that. So this is just like to prove a point. I know this is like a little bit ridiculous and fancy, but nevertheless, like I am trying to prove a very concrete point here, which is like we don't have to do things that are hard always. Like sometimes it's good to take a step back, reconsider what we are doing, and then like be like, okay, are there better abstractions for this? Are there better ways that we can think about this stuff? For some time, often the answer will be no, and that's fine, but sometimes the answer might be yes. And it's worth the time spent in doing that. Okay, so there's my, I still have my stupid high horse. Let's continue on the coding part here. So we now have the row column openings, which gives us this cool, row openings, column openings, and their proofs. It's just a big struct, which the verifier is going to be sent. Let's make this row, this column, and now we have row call. Let's call it RC openings. We don't need this now. We do need our prime. And the RC openings here is going to be, this is like still a terrible function signature for what it's worth. I really don't like it, but we will deal with it later. It needs to be a ZODA row call openings T. So these are all the same T, which is cool. Okay, so for the openings, let's do first. Let's like actually get the verification here. So we have S row here, we have S call here, we have XS is YR. This is WR prime, and let's do. So, by the way, this is obviously like insanely inefficient, right? Like we're encoding the entire thing and then just taking a subsample. In reality, we could just take a few inner products. Same thing here. Cool. So let's get XS and XYS prime. XS and YS prime is the verifier encoding proof, right? I believe, no, actually not the verifier. It's in the ZODA row openings. So RC openings, row openings, and RC openings columns. Cool. And I'm going to remove this prime here because we don't need it. And this should pass what we have so far. So let's do verify. Okay, so what do we need? We need a verifier encoding proof. So let's get that. The encoding proof. Actually, I think at this point I'm going to start actually making a script. So a script, I'm just going to do an examples directory. This is going to be out in the big boy, and then we are going to do, example or ZODA or something. Okay, so we're going to do great using binary, or not binary, yes, actually binary fields, and then using ZODA tensor. Cool, we're going to start with some data, so data to be committed to. This is going to be rand of, let's say, dimensions are going to be n equals 2 to the 10. In rate is going to be equal to 4. And we're just going to do this. So binary lm32, great. And then we are going to get prover and verifier commitments. So again, the important thing is that the prover, the verifier is only going to get things that are meant for the verifier. So these are like verifier commitments, and the prover is just going to keep the things that are for the prover. So prover com, verifier com, great. And then we don't need this equals. Great. So for fun, and what's cool about this thing is you can just press Control Enter, and it will run it in the REPL. So we don't actually have to use the REPL directly. We can use it through a script because you can just run lines of the script automatically, and those get pasted in there and all cool stuff. Okay, so that's the commitment. So what does the commitment do? As before, it does this encoding, it builds the Merkle tree, and then it creates the commitment, and then the verifier commitment is going to be sent to the verifier, which are just the roots. So, and just for fun, show size of, verifier commitment. So this is the thing we care about are the things that are sent to the verifier, so let's just keep track of their sizes in our fun script. And here we can see that the size of this thing is 16 bytes. Ooh, actually, is that right? It is not. That is size of. Good. Cool. So should be 1. Should be great. Okay. So now if we do this, it should. Yeah, okay. It's going to complain at me because I did the thing. But luckily, we already have all this, so we can just do this. Okay, sorry, I've just selected all of it, and I'm just running it on the console. Because I did a thing where I overshadowed a function in a really dumb way. ZODA verifier commitment is not defined in ZODA tensor because I haven't defined it that way. What if we don't do stupid stuff? Challenge impossible. Okay, let's try this again. Great. Cool, and now we can see that's actually what we expect. So it's 2 hashes, each of which starts 32 bytes, so we get 64 bytes. Great. Okay, so that's cool. We've done all the neat stuff of the commitment. Let's do an encoding proof. So the encoding proof actually could technically be part of the commitment because we're gonna use uniform randomness, but there's something a little bit weird here that I need to be careful with because in reality, we're not going to use uniform randomness for the randomness here. We're going to use log randomness, and the reason why is because we need to do certain like products and valuations. But for now, I'm going to totally bullshit this, and it's going to be uniform randomness. Get randomness, usually from PHMIR. Wow, very nice. And then it's going to be R. Is this? I'm just going to say R in both sides, which is probably dumb. That's fine. And then what we are going to do, and just prime equals R for now. That's obviously dumb, so don't do that. Also, as it says, don't be dumb. And we are going to prove the encoding proof. So now we're going to get the great. Glad we could all agree. We're chilling here. All right, and then finally we're going to sample some rows calls. And I'm just going to do the dumb thing, which is collect set sort of rand 1 to n times in rate. And then we're going to collect 150 samples. Yeah, we'll reject some of it. Doesn't fucking matter. Actually, funnily enough, the bounds that we have, even in spite of the fact that we do this and we throw out some samples that are that collide, actually it's totally fine because in our proof we're actually not assuming that the samples are drawn without replacement. So actually this is doing this with 148 is actually completely enough, which is very weird and very silly, but that's fine. Okay, so from this, let's just do this. It gets done twice, so we do S row, S call. So it's actually totally chilling, and we are going to do row call openings. So row call proof equals row call openings for commitments. S row and S call. Does that seem right? That looks right. Great. And then finally, just for fun, let's run this. So we have get randomness. We already have a commitment. We cannot assign it. Oh, I did not mean to do that. Oops. And proof. Great. Let's also make that print nicely for now. Oh, nice. Wow, it really knows what I want to do. That's very weird. Great. Do like. We just do this. Pardon me. Great. Oops. So let's do that. Great. We got a ZODA encoding proof. And then we should just be able to run this directly too. So we got row column openings as well. Very neat. We should, do the thing we expect to do. So now I'm just going to copy this. So, okay, first things first, let's even just write what the size of this commitment is. So if we do this, we do based on the size of. Great. And I think that is good. So if we do, let's put this back up here. So let's run the size of this. Cool. It is, oh, right, and we can even do this as base format bytes. So 1.176 megabits. That's the whole proof. So it's cool. There you go. The proof is, I mean, it's large simply because of the fact that we're also doing sampling down to 2 to the negative 10 or 2 to the negative 100. We don't really need that for data availability, honestly, but for the, so the size of the witness is x tilde. Total size is size f is, it says here, 4 megabytes. So not a very big witness, not too small of a witness. Overall, it's kind of fine. Let's, it's funny because if we were to do this actually with 2 to the 16, it would be even smaller. So let's actually start with that just for fun. Also, this is, by the way, a thing that probably would make a lot of things explode if you did it in many other languages. So here I'm just going to change the type of the element to base binary element to the 16. So in other words, the basis now over a smaller field, right? And let's see, size of x tilde is going to be smaller, obviously. Oops. It's going to be 2 megabytes. But if we, on the other hand, make this, so it looks like the proof of the row column is 600 kilobytes here. If we make this, so let's say we want to do, just for now, let's do the Ethereum target in 5 years, which is going to be, I believe it's 32 megabits. So it's going to be 32 times 2 to the 20 bytes. And then the field size is going to be 2 to the 32, which means that it is 4 bytes per field element. So that's going to be 8 times 10 to the 20, which is 2 to the 23. That's really annoying. So let's make it 2 to the 24. Why not? We're making it, we're going big, we're going home. So 2 to the 12, so 2 to the 24. So actually this is going to be 64 megabits. Sorry. We're doing this over 2 to the 16, so it's going to be 2. So 32 times 2 to the 20 over 2 is 16 times 2 to the 20, which is, 2 to the 24. So 2 to the 24, which means that that's the size of the whole thing. If we squish it, so 2 to the 24 binary element 16s, if we squish it down to a matrix, that means the size of each row of the matrix and the column of the matrix is 2 to the 12. That in turn, which is sick and also very cool, means that the proof size for this interactive proof is going to be relatively small, ideally. I'm sorry, it needs to compile and all sorts of nonsense, so it will take a little bit. But actually, why is it taking so long? It's very weird. Okay, what is happening here? Oops. So let's try this one more time. So this is the Ethereum target using a rate of 1/4 on a single thread of a laptop with a terribly optimized implementation because I'm not doing, I'm allocating everywhere. I'm not doing anything interesting here. We are committing to big matrices and all sorts of weird nonsense. It is weird that it is taking this long, which tells me something is screwed up. This should take a few seconds at most. And a few seconds including loading time, including compiling time, sorry. Okay, so if we do this for a 2 to the 12 binary element 16, the total size, not small, not large, it's about 2 megs, right? So, right, because that's going to be 2 to the 24 elements of size 2 to 16, which are 2 bytes each. So if we do, base stock format bytes, this will be 32 megabytes. So anyway, so for a proof of 2 to the negative 100, the total proof size is going to be 2 megs. Obviously, we don't have to do 2 to the negative 100. I mean, let's do instead standard, light node proof size. Maybe we do 1 in 1,000, so 2 to the negative 10. So what is that going to be? That's going to be negative 10 divided by log base 2 of 1 minus the rate, which is 1/4. So that would be 24 samples. If we do 24 samples instead of 148, the proof size is now going to be 300 kilobytes. So that's pretty good. Look, man, you want to know that your thing is good down to 10 bits of security and you're doing it on your phone. You're totally chilling if you just do a 400 kilobyte proof. Okay, so for what it's worth, I am missing one part of the proof, which is somewhat important, not super important, but somewhat important. Which is the rusted up. No. Well, you should listen to the annoying parts of this whole bit where I am explaining why I actually, not using Rust for this. Using Rust for this is actually a bad idea. But thanks, Francesco. So, okay, yeah, so the final thing is what's the size of the encoding proof, which, let's figure it out. Based on size of, it varies here with a bunch of stuff, but it's fine. If we do that, and we write, a show, nice. 16 kilobytes. So the total size is tiny. I mean, here, what we're saying is if you're happy sitting around at about 2 to the negative 10, so in other words, 10 bits of security, you can get you're totally chilling and can get away with roughly, 400 kilobyte proofs. And this is like, again, the proof generation and all that stuff, 90% of it is encoding time. It's done on a single thread of a MacBook Air while I'm streaming. It's very small. This we could do today, no problem. Okay, so we'll bump it up to gigabytes. Obviously, you have to do a slightly more optimized implementation over this, but the point is, look, you want to prove that a 2 to the 32 block has the right data and has been encoded correctly and all the stuff, and you want to do it on your phone. You want to do it on a light node that runs on your phone, download some proof or whatever. You could do it right now. Just literally, and this is in Julia, so it could be way faster. Single threaded could be way faster. You could do it right now and have essentially no problem. Okay, so finally, we now have the row column proof, which is the last thing we needed to prove the rest. So which is this verify bit. And to do that, what do we need to prove? Well, we're going to prove these. For now, I'm not going to prove these opening paths. These things actually don't matter. Before I screw it up, let's do that, and let's do verify. So that's verify the commit. I don't even know if that's right. I hope that's right, but I have no idea. So let's just, we're Livecoding here. All right, cool. Read Solomon is not defined because I have not defined it. Great. Let's try that one more time. Read Solomon, not, oh shit, we need to run this. That's probably a good idea. Verify is not defined in main because I have not exported it, have I? Let's do. Cool. Okay, so where are we at now? We have ys prime times this does not equal the encoding of wr prime of s because I am looking at the wrong thing, I suspect. So where are we? We have X. We then construct proof of commit X times R, proof of commit X tilde prime times R prime, and then we construct the first n rows, and then we get the S columns. So this should be fine. And then just for fun, let me bring this back to 148. So we're chilling here. I have the row called proof. S row, encoding proof verifier commitments. Is that all right? I'm going to do this for now. Just so all right. It looks like it is right. So let's figure out where we are going wrong here. It'd be very cool if we did not have that problem, but alas, here we are. R prime, this is transposed, this is good. We collect the transpose here. So, all right, what is this? All right, where are we at? Oops. These mostly match, but what isn't matching here? There's something weird. What the hell? What is going on? Let's write this. Oops. Oh, these all match. What the hell's going on? Oh. This is because I am a special kind of idiot. Sorry, I was checking that they were equal and then erroring if they were equal, which is good. that is not what we're supposed to do here. Okay, cool. So we're good. Okay, great. Good. Okay, so verify mostly runs. Now the last thing we need to do is actually check that the the verifier commitments and the openings are good. So let's do that, which is S. I'm gonna move this back up here, and we finally need to just open these things. So if I don't finish, it's about 10 minutes, and I go anyways. So it's fine. You go pick up a shirt for my wedding. Let's do this. Okay, so we have verifier commit. Where are we at? I kind of just lost my train of thought. We are okay. We need to verify that the actual openings match. So we have the row opening proofs and row and column opening proofs. So let's do that, and we can do that by doing verify of Merkle root, the match Merkle proof, the depth, the leaves, and the leaf indices. So I'm gonna hard code the shit out of this for now because I am lazy. Actually, I don't even need to because that is part of Reed Solomon. If I actually understand, I'm using Reed Solomon, RS. Ooh, let's make this. Yank this. Put this here. This RS. Cool. this. And we should be able to do like block length, right? RS. Look at that. That's so neat. Fog block length. RS. Wow. So good. Look at that. Beautiful. Okay, so that'll be the depth of the tree, obviously, because that's the size of the encoded columns. So tree depth equals block length RS. Cool. And then we could just do verify batch medical tree proof. Verify. Verifier commit the Merkle row roots. So I'm gonna check. Oops. Check the rows. Row. Right, row opening proof. Each row access. S row and tree depth. Wow, I think that is right. No, it is not right. Let's see. We have the first two, then the next needs to be named keyword arguments. Depth equals tree depth. We have leaves. Equals each row access. And what do we call those indices? Leaf indices. Leaf indices equals S row. Great. All right. We should be able to verify those now. Oops. Field data type has no type verify. And why is that? Do we have a ZODA tensor data type? Oh, it's not patched. Shit, it's patched tree. Cool. And we have false, which is bad and not good. Cool. Let's see. I am probably screwing this up pretty badly. Leaf or leaf and leaves. We should just do dot here. Copy. Great. Row root, row opening proof. Let's see. Where are we here? That is good in sorted order. I don't think it's gonna be happy if I do that. Okay. The leaves are each row of XS. That's fine. These are the ones we're getting, and we're getting the openings for. We have the row opening proofs. I really hope I didn't screw this one up. Oh, right. Last but not least, we are sending one to N, so we actually need, like in reality, the opening proofs that we need to get are actually the encodings of each of these. So it should be encode RS each row, and now we're Gucci. Look at that. Beautiful. All right, and with that, let's do the same thing for the column openings. So the reason why is because the verifier doesn't need to send the whole row. The proof doesn't need to send the whole row. The verifier already knows that if the proof checks out, the whole row is good. It's like an encoded row. So all it's going to do is it's going to, instead of sending the whole encoded row, it can just send the message, right? And then the verifier can simply encode the row itself and then check the Merkle commitment to the big matrix, which saves, in this case, a lot of space, because if not, the prover would have to send 4x the amount of information, but it's kind of redundant information because by definition it's an encoded thing. So we just do call proof, call opening proof, and then do exactly the same thing, just over call root, call opening proof, and this is going to be each row of ys prime, s call. We should check that. Beautiful. We are so back, baby. And last but not least, we now just need to check that the inner products are consistent with each other. So if yr transpose r prime is not equal w prime transpose r, then sorry, proof doesn't pass. And we are good. And that's all of ZODA. That's the entire thing coded, done in 126 lines of not the cleanest, but clean enough, Julia. And we can remove all these little proof ones and call openings ones and all this nonsense because we are pretty much set here. And actually, so let's see what it is when I remove that. And I'm going to remove this because I can just do this. And this. Yeah, 117 lines. And we have some comments and all that nonsense that I should have probably done more by AI assistant coding, but this is more fun this way. And that's it. That's the entire bit of ZODA. If anybody has any questions, as always, just feel free to comment. Comment, like, subscribe below. Hit that like button, smash that like button. And I'll see you next time, whenever that is. Thank you all for joining. Very fun. It was very weird. I'm not gonna lie. I haven't live streamed something since back in the days I used to play Counter-Strike. So this is rather interesting. But yeah, thank you all, and good luck out there.